So in today's class, we'll be looking at one of the classifications that we went through yesterday in a little more detail. So that's essentially the type of the source of the load that comes in on the flying vehicle structure, and we will also see from that certain motivation into typical construction geometries that are used in flying vehicles. And so most of our course class today will be devoted to this particular thing, because as I said, the geometry is a very critical thing, equally if not more important than the material. So this is something that we discussed in a little less detail yesterday. So we will look through it in a little more detail today. Of course, flying vehicles come in a very large class. So you have both those which fly in atmospheres like that of the Earth, and those which fly in space. Pretty much you have vacuum, or you could have in atmospheres such as Mars, where it's highly rarefied, the densities are much lower, the pressures are much lower, etc. So where the air loads are very less. But for most flying vehicles like aircraft and helicopters which fly on Earth, this becomes the dominant load, the airflow, and that's what we would like to focus on to start with. Okay, so airflow, as you can see, typically, as you are aware from the other courses that you've been doing in AE as well, where are the pens? Okay. Is it all right if I erase this? It's part of your homework, I guess. Yeah. Is there a clean duster or eraser? That's okay. Used to be one. All right. That's okay. Yeah, that'll be good. Yeah. Sure. Please, thanks. Oh yeah, sorry. You can call him back. I look better without this. Yeah. So, as you know, the dominant loads are, of course, the lift force, the drag force, and the pitching moment, for which the convention is positive nose up. So we will denote that by M. Okay. So LD and M, and that's for the aircraft as a whole acting through its CG. But the primary contribution for the lift, of course, comes from the wings. And that's essentially what we would be interested in. So if you're looking at structural analysis, as I said, analysis is breaking into parts. The first breaking up comes in terms of the overall component itself, the fuselage separately, the stabilizers separately, and then the wings separately, and each half of the wing separately. So then we start treating one half of the wing as a structural component. That's what we call that. So a wing is an example of a structural component. Is a terminology component that is used in the industry both Airbus, Boeing, and many other aircraft manufacturers use that. So examples would be wing, the fuselage, the horizontal tail or stabilizer, and the vertical tail, the other stabilizer, right? So predominantly, of course, you have the engines and other things, the pylon, the way the engine is attached, etc. So that comes in as well. Okay, and the structural analysis for these aerodynamic bodies, namely the wing, horizontal tail, and the vertical tail, are pretty similar to each other, and that's where this first classification of airflow comes in as the dominant load or predominant load, right? Not that it doesn't experience the other loads, so because it has its own self weight. For example, it has on the wing you might be mounting the engine, so the weight of the engine, the thrust from the engine, because of that the force, and therefore the moment about its route. So all those things will also be there. More often than not, you have the fuel which is stored in the wings, and therefore you try to see the weight distribution of that fuel as well, and that changes over flight from takeoff to landing. It reduces, and that's how you typically will work. Any guesses on if the fuel is stored in the wings? It typically is not stored in one tank, especially for larger aircraft. It will be stored on, let's say, multiple tanks. Let's say there is some fuel here, another over here, etc., somewhere in between. So let's say this is number 1, number 2, number 3. So let's say for an arbitrary aircraft, you have on either or half of the wing, the port and the starboard. So you typically call your left as port and the right as starboard, as will be familiar. So let's say you have something like this. It's quite clear that from the point of view of symmetry, you would want to start spending the fuel on both halves of the wing, starboard and port, up to the same, about the same amount, so that the reduction in weight is the same. Otherwise, you'll have a weight imbalance that is coming up. It might be a very small moment compared to the moments due to the lift, but nonetheless, that's something that you need to be concerned about. But the question that I'm asking you is now is, between these three tanks, which would I want to finish first and why? Which should I start emptying first and why? Second one? Center? Okay, okay. Reason for that?
Because then, like, if you're draining out to center, it still balances the weight between inner and outer things.
Okay, so you're talking about within the wing there's some kind of a balance, but what is more important is the balance of the entire aircraft, right? So the wing is attached to the fuselage. We want the whole thing to be balanced, right? So which do you think? Yeah, third one. Okay, so this one. Why do you think that that is?
Because the distance matters in focus.
Okay.
Right? So the statics problem, say like the farther you are away, right, you want that weight to be less from the
Okay, okay, that's a good point. Anybody else have any difference with that?
I probably actually switch my answer to 3. I think that makes sense.
You're moving to that as well. Okay, becomes that's teamwork. Anybody else have a difference of opinion or any additional reason for or to join their team?
I think you might want to work start from number 1 and then work your way outwards. Or like keep that balance.
Okay, okay, okay. Why is that, Nafis?
It's similar to their reasoning where you want to keep the moments like stabilized on both sides.
Uh-huh.
I think that's
The reason which, and I mentioned, the logic is important, but you would need to think a little more intricately on that. Before that, let's get Evan's.
Well, basically, at the same point, I guess 3 because of moments.
You say 3 as well?
Yeah.
Okay. So who do you think is the winner, Hafiz or the team of 3? As I said, no competition between you guys, but I'm glad you're thinking on the right in the right direction, because you talked about the force and therefore the moment arm. You want to, because the main difference between these 3 is in terms of how far are they away from the CG, right, of the aircraft as a whole. Okay, the farther they are, the weight of the fuel in that is going to cause a larger moment, right, because it's the force times the distance, right. But the point you missed out, and everybody else joined you, is the direction of that force. Which direction is the force acting in? If let's say the aircraft is cruising, okay. So remember, we are talking about the weight of the fuel, right? So just like any other weight, it would be acting downward, vertically downwards, or towards the center of the earth, to be more precise, right? So if that is the case, what is the direction in which it is trying, making the wing try to bend? It's trying to make the wing bend in this way, right? For the wing tip to go down, right? Irrespective of which fuel tank it is in. The one in the 3 will make it go down more, okay? But is that the dominant load on the wing? What is the dominant load on the wing?
What do you mean by dominant?
Dominant load in the sense which is the largest load coming on the wing, right, when it's flying. Drag, okay. Is the drag more than the lift? You know of typical L by D ratios from your aerodynamics courses for an aircraft or for a wing or for an airfoil even, which will eventually translate to your CL by CD.
The lift should be higher.
Yeah.
Lift is much
Yeah. So usually the lift is much higher if the design is good enough, and which most aircrafts are. So if you choose the good airfoil, obviously this will be large, and in fact it goes to a large value, a particular value of the angle of attack. You can plot CL by CD versus angle of attack. That's for an airfoil. Then you can do for a 3D wing, and then for the aircraft as a whole. Even after you do that, this will remain greater than 1. Okay? So this will be a value which is greater than 1. Okay? So between these loads, it's clear that the lift is the dominant load over there. And the pitching moment, remember, is more like a torque that is applied on this, because it is the tip is twisting because of that, right? So that's essentially because these are assumed to be acting on the loci of what we call as the mean aerodynamic center. Okay, so there's the aerodynamic center at each chord, and then you're essentially joining them up, you're getting that line. Okay, so you assume that because the actual way in which the air loads or the load due to the airflow is acting is by the pressure distribution on the upper surface of the airfoil and the bottom surface of the airfoil. It's the resultant between them which is causing your lift, and then in the direction which is perpendicular to the velocity of the aircraft, and then parallel to the velocity of the aircraft in the opposite direction, you would have the drag, mostly because of the pressure difference between the front and the back, but also more importantly because of the shear integrated over the airfoil cross sections. In other words, if you take at some point, I'm cutting this, let's say, so if I cut this, then this is how this would look, and you would see that this is the aerodynamic center. You have your lift which is acting here, the drag, and the nose up pitching moment, M. Okay, now these are the resultants. Okay, so in your statics course you would have very frequently found resultants before you try to get to some solutions, and the actual thing, the way it is happening on the same airfoil is, though I've drawn it in a different shape, is that you have some kind of a pressure distribution at the bottom which is much more than the pressure distribution on the top. So you're essentially having the difference between them when integrated over the surface area, which is going to be causing a upward lift, net upward lift. Similarly, you also have, of course, the pressure distribution over here, and that's going to cause a little bit of drag. But the more, especially for lower Reynolds numbers, you will have, based on the boundary layers that are there's a shear because of the airflow, and that's how you get it. So here the definition for lift and drag is that you have the V infinity of the aircraft, and because of that, perpendicular to that, when you're resolving all of these forces perpendicular to the velocity, you get the lift. So it need not always be horizontal and vertical. Drag and lift need not necessarily be horizontal and vertical. In cruise flight, of course, it will be, but depending upon whether it's climbing or doing any maneuvers, etc., it's always parallel and perpendicular to the velocity. Now, these things, though they are all aerodynamic aspects, very, very critical from a structural analysis perspective, because the inputs that we will be getting from the aerodynamicist or their team of aerodynamicists is essentially in terms of what is happening at the aerodynamic center or the mean aerodynamic center, and it's these values that we'll be getting, not the actual distributions, though if it's necessary for some local designs, we can ask for it and get that. Okay. Now, keeping that in mind, already we saw drag is smaller compared to the lift is large, and what is the lift typically equal to? Let's say in cruise flight, what is the equilibrium condition? What do you want the lift to be equal to if it's cruising at a altitude, by which we mean that it's maintaining its altitude, it's maintaining its speed. Okay, so lift equal to weight of, right. So if I call this the weight of the entire aircraft to be WAC aircraft, so then obviously in cruise you would have weight of the aircraft. But what is the weights that we are talking about in 1, 2 and 3? It's the weight of the fuel, right? So that's WF. Obviously WF is going to be much, much smaller than your WAC, right? So depending on the aircraft, how the fraction will change, but essentially it's the fuel weight fraction that is there, so which is a smaller fraction. So remember that the lift that is acting, it is getting divided between the two wings. Of course, there's a tail contribution and all that, horizontal tail, and there's some, could possibly be a negative contribution also sometimes from them or from the fuselage, but the dominant lift is coming from the two halves of the wing, port and the starboard, right? Now that's equal to as much as the weight of the aircraft, whereas each one of these is a very small fraction, and that lift, remember, what is the direction in which it is causing the wing to bend? Is it going to be wingtip upwards or wingtip downwards? Right. So it's going to push the wingtip up, right? Whereas these weights are going to pull it down. So actually it's a huge structural advantage for us to have the fuel over here, because we want a downward moment. In other words, it's a huge lift which is trying to push my wingtips up. Now if I have some weights on this, like the engine, the fuels, etc., then it's trying to give a counterbalance, it's trying to pull down. On the ground, when the aircraft is not flying, it's the other way around, so the reasoning that you came up with is absolutely valid. But when you're going up, you really want this to create that moment so that there can be some alleviation of stresses, in other words, reduction of stresses close to the root, right? Because this is the most stressed portion where the fuselage is attached to the wing. All of the loads that are coming from the wing, the lift, drag and the pitching moment, they're all going to eventually cause huge stresses there, which is why you have a much larger cross section. So this airfoil will not remain the same throughout, both in terms of the type of airfoil and or also the chord and the chord C and the thickness T. All of this will be typically much larger. C and T will be much larger at the root compared to what it will be at the tip. So in other words, C at the root will be C for the wing, at the root will be smaller compared to larger compared to C of the wing at the tip, okay, the chord. And similarly, your thickness of the wing at the root is usually much larger compared to the thickness of the wing at the tip, right? So now, if you want a larger moment here because of the fuel weight, obviously you want to spend this the last, right? You want to spend this the first. So the reasoning wasn't there, but Nafis wins as far as this is concerned, right? So is this clear, or do you have any doubts on this? Okay, it's just an interesting fact, but these kinds of little things will help us understand the overall picture in terms of what are the forces, what are the moments, how there are many different sources which will be dominant, which will be very small, and therefore which is something that you need to be concerned about, and in which phase of light. As we saw on the ground, the story is entirely different, okay, but that's not the critical thing. What is more critical is when it's flying, at least from this point of view, and therefore this is how you would start spending. So you would start spending the fuel in the same order in which I numbered them. So this is number 1, number 2, number 3. That's the order in which you would start spending your fuel, so that the moment alleviation, stress alleviation would continue, right? So that's the dominant load coming from the airflow, but that's not all, right? So the next thing that we'll be focusing on is the so-called concentrated loads due to the landing gear, due to impact, due to controls, etc. And concentrated load is just a theoretician or a mathematician or an academician's wish. Never can you have a concentrated force, because if you have a concentrated force, then you would have, at that point, the boundary condition would be, because the concentrated force divided by the area on which it acts, concentrated by force by definition is acting on at a point which has zero area, which means force by area is going to tend towards infinity. Obviously the material would have failed much before it tended to infinity. So it's quite obvious that it's not possible. Just that we want to, what we want to say is, compared to the other areas that are associated with the problem, it's a very small area in which it acts. So in other words, practically how you apply a so-called concentrated load is quite different. So in this case, for example, the landing gear, the way the landing gear is attached to the belly of the fuselage or to the under portion of the wings is going to be a fairly complex arrangement in terms of how it is attached, and that's obviously not at a point. It's going over a small area, but that area is definitely small compared to the overall surface area of the wing, right? So that's what you need to see in some sense of a relative sense rather than absolute sense. When you say something is zero, it's not actually zero, but it's small compared to something else, okay? When you say something is infinity, it doesn't mean it's really infinity, it's very large compared to something else. So that's the terminology which we commonly use in all aspects of engineering, and that is applicable over here also. So compared to the lift distribution which takes place over the entire chord and the entire span of the wing, the load due to let's say the engine being attached at a particular point, the landing gear being attached to a particular point, or the controls from the for the aileron and the flaps that are there. You're familiar with where the flaps are and where the ailerons are? The logic followed is very similar to the weight ordering that we saw in terms of the fuel tank, right? Because you want, whenever the aileron is operated, you want a large rolling moment, and therefore you want the ailerons to be farther away from the CG of the aircraft. So you typically have ailerons closer to the tip, and the flaps which will be closer to the fuselage, because that's operated in a symmetric way in order to increase the lift for your takeoff and landing, whereas your ailerons you want to operate them differentially so that one creates a force upward, the other wing goes down, and therefore essentially the aircraft is rolling, right? So the same logic works. So this is a very important thing to remember, that whenever you're talking of moments, be it torques or bending moments, there are two things associated with it. One is the force, the other is the moment arm. So you can sometimes play around with that during your design. Even if the force becomes large, see if you can reduce the moment arm or the other way around, right? So that's one thing, the landing gear and the engines, but there can, and the controls for the aileron, similarly in the horizontal tail, the elevator, and the vertical tail, the rudder that is there, right? So those forces are also typically through actuators which are within the wing. So you would have seen, if you have a window seat close to the wing, then you would have seen during takeoff or landing, when it opens up, you would see some of those actuator servos, arms coming and actually causing this deflection of the flaps, and that's essentially at those locations it's acting, and that area is small compared to the overall wing area, and therefore we can treat it for most practical purposes as concentrated loads for the overall design. But when we are designing the joint itself, obviously we have to look at it the way it is applied, and this is what I mentioned as Saint Venant's principle during yesterday's class as well. Where the way the actual attachment of the load causing structure to the structure that we are interested in doesn't matter for a first cut analysis in the interiors, but close to where the attachment itself is there, you would need to see exactly how it is attached. For example, it could be through a bolted joint, there could be multiple bolts. You need to take the actual bolt loads and how the distribution takes place around the circumference of the bolts, etc. So all that will have to be accounted for closer to the point of application of the load or any other boundary conditions that you might have. Whereas when you go towards the interior, really doesn't matter. You can, for all practical purposes, you can take the resultants of those just like we did over here, and then everything will be fine in terms of the calculations. Then sometimes you might have the impact, as we discussed in the yesterday's class, about bird hits and the maintenance kind of situations where there could be a tool drop at some location, because of which there will be impacts, and those are also, again, the impact happens over a very small area. For example, if you are dropping a hammer, it's the cross section of the hammer which comes into contact with the aircraft or a part of the aircraft, which is the area in which this is acting. That area is very small compared to the overall area of the aircraft, and therefore that the aircraft occupies, and therefore it's more like a small size in which it is occurring. That is from a spatial point of view, but the impact is also from a temporal point of view. In other words, not only from the perspective of size in x1, x2, x3, but the size in terms of t. So it's over a very small duration that it's happening. So that's impact. So many things, very interestingly, mathematics helps us understand in a much better way, because we always tend to think, because based on our own experience, that spatial behavior is very different from temporal behavior. But there's a huge analogy between the spatial behavior and the temporal behavior, because of the fact that all three, x1, x2, x3, and the time are all independent variables. Okay, so if we have understood in a statics problem how things vary with respect to x1, x2, x3, and the mathematical model is very similar in terms of the behavior with respect to t, the intuitively we can get the understanding of how it would behave with time in a dynamics problem from understanding this, and becomes more clear in a beam problem when you will have x2 and x3 drop off as the cross-sectional coordinates, which are very small, and only x1 will remain. So there's one space coordinate, one time coordinate, and therefore you can very clearly see the analogy between those two. So when we get to some of those equations I'll point out some of the parallels there so that you can understand and appreciate the analogy, because there you're trying to understand things from a much more holistic perspective, from a philosophical perspective, and that really helps in terms of your even your practical decisions on actual applications also, because then you have the overall picture and you're not making what I called yesterday as ad hoc decisions, right? So that's the second category. Then we move on to the third category, which is self-weight, right? So which is what we talked about earlier was the weight of the fuel. Now it's the weight of the structure itself, the weight of the entire aircraft, and that is again, though for certain purposes it's okay to talk about a CG and then the weight of the entire aircraft WAC acting through the CG. In an actual problem for a structural analysis, that is not good enough. You have to know the weight of the wings, different skeletal structures, the fuel, where it is located, all of that, because it's not just the total weight that matters, but it's the weight distribution that matters, how much weight is where. Okay, so all of this will cause different kinds of stresses, because the moments will be different, because the forces will be different at different locations, right? Why the forces will be different is, for example, if you take the because of this fuel tank, whatever the weight it is causing, we talked about moments already, the difference between these three. But even if you talk about the force due to that, you would see that anything outboard here will not be experienced, because it is a free end, will not be experiencing these forces. Anything inboard between 3 and 2 will experience only 3, the force due to 3. Similarly, anything between 3 and 2 will experience, between 2 and 1 will experience only the force due to 3 and 2. So, and so on and so forth, right? So, these kinds of things are important, not only because for moments, because there's a moment arm there, but also in terms of the forces, how they're going to cause or not cause a stress will depend on their location. So locations are very, very critical, apart from the magnitudes of those forces or the force distributions, right? So that's self-weight. So in this case, you see that we already discussed, because the stresses are large here, you have a larger chord, larger thickness. Obviously, the weight per unit length will also be large over there, whereas the weight per unit length will be the minimum over here, right? So if you plot the weight versus the span direction, you would see that it will start with 0 over here and slowly increase and become larger over there. And very interestingly, the lift distribution is also very similar. So in other words, if I call this direction as y, let's call this as x, and you have x, y, you can put z in this, though usually the convention is to y to take along the starboard and z downwards. Just for this practical purpose that we are talking about doesn't matter. Here we are talking about versus y, the various loads that come. For example, the lift distribution would be somewhat elliptic in nature. So this is your L. So these are all the loads, and then you would have certain concentrated loads which are coming at certain locations because of the engine or the fuel tank, etc. So you would have some of those as well. And then the self-weight. We're talking about the self-weight now. The self-weight will also be in the downward direction, and that would also be somewhat like this, right? So in other words, it's 0. We are talking about in these cases the forces that we are talking about here, the dimension is meters, let's say. This would be Newton per meters, the force per unit length. It's a distribution that we are talking about, and that distribution will be like this, approximately elliptical. Of course, there are, you would have studied probably in other courses, there are much better models which can predict it much more accurately, the lift distribution, depending upon the airfoil cross sections, how they change along the span, right? Now, so this is the self-weight. Whereas this could be an engine and fuel tanks, etc. anything which is mounted on or within the wing, that is going to have its own weight and therefore being pulling it down. So you can see that the lift is much larger compared to any of these things. In fact, it will be much larger than what I have depicted this is not to scale, and therefore you would see that will be the dominating thing. But anything which can come in the downward direction is going to make an alleviation over there, right? Next. The fourth source that we'll be looking at is an innocuous thing. Most people tend to ignore that, at least in the first cut analysis. But depending upon the kind of materials that you're using, etc., that can become very critical. In the engine, of course, the temperature variations, it's quite obvious it's going to make a huge difference. But even in the rest of the aircraft structure, be it the wing or the tail or the fuselage, you would see that if there is a variation in the humidity, for example, it's very large when you have aircraft which are flying, which are, let's say, amphibious kind of aircraft, which fly in more like a boat when they are on the water, and then they can fly as well, just like any other aircraft. So their exposure to humid atmosphere is almost direct. But even otherwise, you know that the atmosphere itself has a certain level of humidity, and depending on the season and the place, certain places and certain seasons will have very high humidity, relative humidity going all the way close to 100%. And this can have an effect in terms of the material that is there. But what we are talking about is the load source. Before that, I'll talk about the impact on the material. For example, if it's some kind of steel, there could be a possibility of rust and things like that. So there can be a chemical degradation which develops depending upon the content of that water. Typically, if it's over it's flying over the sea, then the salt water can have a huge impact as well, which is something that was found out to shocking surprise when during the Gulf War, when a lot of the American aircraft were operating in the Gulf regions. The kind of issues that they were facing were something that they had not faced when they were flying within the mainland of the US or other continents, right? So then you would see that these two, the changes in humidity, changes in temperature, can cause stresses due to that, what are known as hygrothermal stresses. Hygro stands for the humidity related stress, and thermal is of course the temperature related stress, and these will cause certain stresses. The other thing is in terms of the degradation of the material itself. For example, many composites which are made out of epoxy matrix can have a swelling. So in other words, the epoxy swells and therefore its properties become inferior. In other words, there's a degradation of some of the required properties like strength or stiffness and things like that. So over age, or many of these could also be temporary things if it's a very small changes that are involved. And so in other words, just like elastic materials get back their shape, this might also happen in this particular case once it's in a drier place and or hotter kind of climates. But more often than not, these changes are larger, and therefore some of these effects would be permanent as well, and that has to be taken into account. Now, as far as the loading source is concerned, why these are causing loads is essentially because of these changes in dimensions which are happening. You can see when something is heated, especially metal, for example, you have an expansion or contraction, and typically you have something called the coefficient of thermal expansion, how much it changes its size by per degree centigrade or per Kelvin for a change in the temperature. Similarly, for a unit change in the humidity as well, there is a certain stress which essentially develops, and all of that is going to cause thermal stresses, so which is something that we need to be aware of. Next is, we already talked about the self weight of the engine, but the engine of course is there for the main purpose of providing thrust, and therefore that thrust force acting through the center line of the engine is going to cause a moment as well, and that's a moment which is opposite to the direction of the drag. So the drag is acting to push the tips backwards towards the tail. If there's a canard, then it's away from the canard. But what will happen in the case of the thrust is that it's trying to push it forward, So the thrust is obviously in this direction. This is the thrust, and that thrust is going to try to push the wing tips forward. Okay, so just like we had between the weight and the lift, we're talking of not the weight of the entire aircraft, but the weight of the wing, self weight of the wing, and the contents of the wing, whatever is within or also mounted on top or bottom of the wing. All of that is going to cause moments in the opposite direction to the lift generated by the tail, the wing. But similar kind of a difference is there between what the thrust and the drag do. And for cruise, of course, the thrust is equal to the drag, but for certain maneuvers, you might want the thrust to be much larger than drag. So another important thing that is part of the overall aircraft design is in terms of your T by D ratios and what you can, or even T by W ratios, the thrust to weight ratio. For some of the more highly maneuverable aircraft like fighters, your T by W has to be much larger than for a passenger aircraft, etc. Okay, so all of that. What I every now and then I'm trying to point out is to bring in the aspects of propulsion, aerodynamics, and controls here to make it very clear for you, though you already know it, is that we can't work in silos. We have to exchange information between the other teams, and all of that is going to make an impact on how we design the structure or how we even analyze the structure, because it has a direct implication in terms of the loads, the load distributions, and how things change over time as well. Okay, so that's as far as the engine thrust is concerned. And again, the engine thrust, remember, in the cruise, of course, your drag and the so T cruise will be equal to the cruising drag as well, because you want to balance. That's the reason why you have it moving at a constant altitude, or more importantly constant speed as well, right? So that equilibrium is there only in the special case of the cruise. In other situations you will have a difference between them, and that has to be accounted for in different phases of flight in order to see how structural analysis of certain components can become critical in various phases of flight depending on the thrust. This is, for example, very critical when you're talking about the pylon or the nacelle. These are the things coming in between the point of attachment to the aircraft, which could be the wing or the fuselage, because some engines are mounted on the fuselage, either the nose or the tail, etc. So it's the balance between those two that you need to take into account for those attachment structures like the pylon, nacelle, etc. You need to make sure that these changes in thrust over different phases of flight are taken into account, so you understand which is the most critical of them all. Next, this is something that which I pointed out in yesterday's class as well. The D'Alembert's force and also the moments that can be caused because of that. The simplest way in which you understand classical mechanics, which is Newtonian, is of course by the simple relation of force is equal to mass times acceleration. And when you go into a more complex kind of situations over here, this becomes a vector, this becomes a vector, and this becomes a matrix, or essentially it becomes a tensor actually, that you will have to deal with. Okay, so corresponding to that, there is also something in the rotationary framework. Just like you have translational acceleration, you have what is known as angular acceleration or rotational acceleration as well, which you would have studied in the dynamics course, for example, denoted by alpha, and that is again a vector, and then there is an I. Okay, so to be more precise, should not call this a matrix because that's actually an implementation. So you know of scalars and vectors, right? So going from a scalar to a vector, you have introduced one direction. If you introduce two directions, and it's because you introduce one direction that you're giving a one underline over here. If two directions are involved, then essentially what we get what is known as a dyadic. Okay, so this is a vector, this is called a dyadic. Okay, and of course there are scalar quantities that you are familiar with as well. So this involves two directions, and another example of that is this stress and also the strain, because both of those are very important things that we will be looking at as we go forward to. And to explain it very simply, in the case of the stress, what are the two directions involved? We already saw. For example, if it's a normal stress, then we have to say which cross section is the stress acting on. So if that the normal to that is the one direction, and then the force also is acting in the same direction, so then you get a stress called sigma 1,1. So essentially it's on the one surface in the one direction, and therefore it's a sigma 1,1. On the one surface you can also have in the two direction or the three direction as well the forces that are acting, so you will have a sigma 1,2, or what we typically call as tau 1,2 and tau 1,3. Okay, so we will get to those things a little later. So now you see that whereas these can be expressed in terms of what are known as components or measure numbers, again, unfortunately, this is something which is very interchangeably used. You know that if you have any vector, let's say v, you can write it as in a three-dimensional space, this way, right? So it's the magnitudes v1, v2, v3 in the directions a1, a2, a3. For simplicity, let's say this is a rectilinear system. That you have, and along that you want the distance v1, this would be v2, and let's say a v3 that is there, and you're adding these things up. So a lot of people use vector components or vector measure numbers interchangeably. You need to make a difference between that, and it's very, very critical. If you're talking about this whole product v1 times a1, then it is a component. Okay, whereas if you're talking of just the v2 alone or v3 alone or v1 alone, these are measure numbers. So these are scalar quantities, okay, which are multiplying the unit vectors, whereas this is a vector itself. So in other words, a vector component is also a vector, whereas vector measure numbers are not vectors, they are scalar quantities. Okay, so that's an important difference that you need to keep in mind when you're communicating either in writing or orally. That will be critical. So coming back to what we were talking about, see, the corresponding thing in rotation is you have a moment or torque, let's say, vector, and then you have a dyadic, which is called as the inertia dyadic. This is the moment vector. That, as I already mentioned, alpha is the angular acceleration or the rotational acceleration. So now this is one way of writing it. This is the classical way of writing a Newtonian mechanics problem in translation and in rotation. But another way in which typically for certain solution processes it becomes easy is to take your right hand side to the left hand side with a negative sign, and therefore set these equal to 0, right? It's actually a 0 vector, but doesn't matter when you're writing 0. It's understood that it's that. So now this becomes like a pseudo force, okay, because it's like all the other F's that are going to be acting. You will have another force called MA. you can treat it like almost like a quasi-static problem. So it's essentially almost like a static problem, because your whatever acceleration was there, that times mass, you have brought it to the left hand side, and you are now treating that as what is known as based on the person who started this, D'Alembert force, right? So similarly, the equivalent of that is the I alpha term in the case of the rotation. Okay, so that's how you typically, that's not typically, that's one of the ways in which inertial loads can be handled. There are many other ways in which it can be handled as well, and they have structural implications too. The other thing is gust loads, as you very well know. Very unfortunately, recently a Singapore Airlines aircraft, there was an accident where one person died in a London to Singapore flight because of the very large turbulence that happened. It's a very, very rare thing in the aircraft or airlines history when something like that happens, because a lot of precautions are taken to prevent that, or rather to not, you can't obviously prevent the turbulence, but how to handle it in the presence of turbulence, both from the aircraft design point of view as well as the pilot training point of view. But sometimes something goes wrong. So you can see from the current news how important those gust loads are, how critical it is for us to take that into account. Okay, so yeah, let's see. It's in that what I mentioned very in passing yesterday is the so-called Venn diagram. Okay, so this is V, also known as the true airspeed. It's the velocity of the aircraft, and then you have N. So let me expand this. You might be familiar with this from of the aircraft, and this is N, which is the load factor. Okay, so apart from this equation, another thing that Newton is very famous for is, of course, the gravitational law that he worked out. So where you see that the gravitational force, which if you call, if you in the simple terms, you know, it's m times g, the mass times the acceleration due to gravity. But if you go further, it's the universal gravitational constant times the two bodies which are exerting that gravitational force between them and the distance between them, right? So whatever is the distance between them, let's say r, so this is one small body over here, which could be the earth, let's say, and there's a aircraft over there. So this is your big M. So this is your small m, this is your big M, and they are exerting force on each other, and that's essentially what you're talking about. And the distance between their CGs is what is written as R over there, right? Now, if you take this F out over here, so you can cancel these out, and so you see that this acceleration due to gravity, which we typically take as on the surface of the earth, we take it as 9.81 meter per second squared, though you might be using FPS units sometimes. This is in SI units, this is what it is, and many people think it's for granted, but especially when you're dealing with not so much for aircraft but for space vehicles and things like that, you have to take the appropriate bodies into account, because this of course doesn't change. It's a universal gravitational constant, but the mass of which body is the dominant exerter of the gravitational load, in other words, which is close enough in the proximity, because theoretically speaking every body should be exerting a force on that, but because the r's will be so large and it's also an r squared in the denominator, that doesn't, most of the bodies will be having only negligible effect. The closest body, massive body, is the one which will be having the maximum effect. Now this small g is therefore going to vary depending upon how far the body is flying from the center of that body which is exerting the gravitational field. So in other words, for example, if it's a launch vehicle, it's all going all the way from sea level to very high altitude, and if it's a satellite which is launched or into a particular orbit, which is a transitional orbit and temporary orbit, and eventually goes into a final orbit, and between them there could be a huge distance difference from the center of the earth, and therefore the small g variations have to be taken into account over there. The other example, of course, I gave you is when you have a satellite which is flying very obviously at, let's say, like a geostationary satellite flying at as large as 36,000 kilometers. So some of these could have could have antennas which are extended onto very large booms. Okay, so you would see that the small g that is experienced at these two ends of the same rod could be quite different. So in other words, you have to take that into account as well. Of course, it's not to scale. Obviously, this is much smaller compared to that. But in terms of the distance that you are away from it, you have to make a note of some of these things. And that's where appropriate accounting for the gravitational loads comes into picture, apart from in the flight, your inertial and the gust loads. The last thing is something we didn't mention so far, is that, you know, in the International Standard Atmosphere itself, you will see that if you look at the variations of pressure from the sea level to a high altitude, you will see a drop, and you would have experienced this when you're doing, let's say, mountaineering or some kind of climbing which involves a change in altitude. You would see that you are reaching lower pressures as you climb higher up, and that's the same thing for the aircraft as well.
Just go over with the graph.
Oh yeah, sorry. Thanks. Yeah. So it's very clear that there are certain limits as far as this is concerned. From an aerodynamics perspective, you know that the speeds, there is a limit. Whereas helicopters can fly backwards, fixed wing aircraft cannot have obviously a zero velocity, right, while flying, right? So which means that this becomes, let's say, a 0-0 origin, or is the origin over here. And then as you start increasing your load factor, n equal to 1 is of course your cruise, when your lift and the weight are one and the same. So this can be defined as L by W. Okay, so in cruise your lift and weight are equal to each other, and therefore the load factor is 1. But because you need to do a lot of maneuvers, even in the case of passenger aircraft, there not a lot of maneuvering is not required because of the takeoff, the climb and descent and landing. All of that you need to have an n which is sometimes greater than 1 as well. So that, in spite of all of that, you cannot go beyond a certain value of n, which is called as n max. There's a certain value that you can't cross, because once you cross that kind of a load factor, your lift becomes very large compared to the total weight of the aircraft. And what that means is, in terms of the acceleration due to gravity, the g's that we were talking about. So the unit for this is of course meter per second in SI units, or kilometers per hour, or knots, whatever you're familiar with. but for the n it's a non-dimensional quantity because it's involving both forces, lift and the weight are both in newtons, and therefore the unit cancels out. It's a non-dimensional quantity, but it's essentially a measure of how many g's that are there, because when L equal to W and the aircraft is cruising at a constant altitude and a constant speed, you are having everybody inside the aircraft is experiencing 1 g load, okay? But when it is climbing or when it is descending and it's accelerating because of that, then you will have either a higher or a lower g. And the thing is that we as human beings, when we are upright, when we are trying to accelerate upwards, there's a blood flow gushing out of our heads more towards the feet, right? So when that happens, there's less blood flow to the brain, okay? And many a times, especially if you are the pilot, you can't make the right decisions in terms of what needs to be done. So even fighter pilots who are trained to experience large G's cannot go beyond a particular point because of the physiological nature and the psychosomatic nature also, because the mind plays a huge role in this, and you cannot handle it beyond that point. So that's your N max that comes over there. Similarly, when you're trying to go down, it's essentially there's a blood flow gushing from the bottom upwards, right? So in other words, the heart pumps a lot of blood towards the brain, and there could be an overflow of essentially blood, and beyond a certain point that cannot be handled. So similarly, just like you have an N max in the positive side, you have an N max on the negative side as well, right? Now the envelope that is there, by which we mean that anything within that is safe, anything outside that is not safe, it's a failure, right? So in other words, if you are outside over here, one is of course the human being's experience, the other is even in terms of the structure, the integrity of the structure. For example, if it's a drone, doesn't mean I can have N max infinity, right? So even a drone is made out of materials, and each one of them have a certain capability that is involved, and therefore, and the joints also that are there between the structural components, all of these can give way. So there will be a certain limit. Not only the structures and human beings or whoever is the occupant of that, including various payloads which might have different kinds of N max that they can experience both in the positive and the negative sense. But even see, most of the aircraft these days, the cost is not the structure, it's the cost, most of the cost is because of the avionics. So the electronics that is involved, the control systems that are involved, the head-up displays and other things that are involved for the pilot, those are very, very expensive things. And though their designs have also improved over time, even today, whatever is the current state of the art, they have a certain limit as well. In other words, the avionics will stop performing to their design, whatever they are designed for, beyond a certain value of N. So from the point of view of the crew, the passengers, the structures and the avionics, the minimum of all of that has to be taken into account, and then you arrive at these bounds, okay? Similarly, you know that from the aircraft point of view, from the aerodynamics point of view, there is a certain limit in terms of the maximum speed that you can fly. Beyond a certain speed, you cannot fly. So all of this is kind of quite clear, and for most practical purposes, it looks like we are approaching almost a rectangular envelope. In other words, you are within that envelope. Any aircraft which is flying inside is safe. Anything which tries to go outside is already in danger, or it's no longer exists as an aircraft, right? So that's essentially what you need to be aware of. But in reality, what happens when both of these are extended, that it doesn't reach all the way to that particular corner, there's a chamfer that is involved over there. So you can't have both Nmax and maximum speed simultaneously. Both are deleterious and they can cause issues. We'll not go into the specifics of all of those because they are quite involved. Similarly, here also you have a chamfer in the envelope. So it's not exactly rectangular. The more interesting thing comes in the other end of the spectrum, because remember, I didn't start all the way from the axis, I started somewhere in between. The reason is that there is another, just like this was an aerodynamic limit, these were all material or structural or human based or avionics based limits. Whereas here, both the left and the right are typically dictated by aerodynamics. The maximum speed that the aircraft can fly at, and also the minimum speed that it can fly at. Helicopters can fly even at negative speed, but fixed wing can fly only at a beyond a certain speed. Are you familiar with this? What is the lowest speed that you can fly a fixed wing aircraft? Exactly, yeah. So stall, what we were talking about earlier, remember CL by CD, etc. So remember that the total lift is given by CL times the dynamic pressure, half rho V squared, which is that we are talking about over there. It's essentially your lift curve slope when you're plotting the lift CL versus alpha. Depending upon whether it has camber or not, it may or may not pass through the origin. Usually you do have a camber, and therefore it goes like this. And so this is a particular alpha naught at which the CL becomes maximum, right? So the way the pilot controls the speed of the aircraft, to some extent there's also thrust control in terms of the throttle, but also it's mostly in terms of the changing the orientation of the aircraft. So by changing the pitch, you're changing the how do you change the pitch? Of course, when you're applying the stick, you're essentially deflecting your elevator bottom or down, and that's causing a moment. And when it causes a moment, with respect to the velocity of the aircraft, it is changing the angle, which is the angle of attack and of the zero lift line of the aircraft. And when that changes, you obviously have a difference in lift, and therefore it's able to go at different angles of attack. And when that happens, the maximum that you can go to is, as you said rightly, is this stall. So we call this as alpha stall, right? And that's also corresponding, because of this particular equation that you have. Let's say you're cruising, in which case lift is equal to weight, and therefore this is equal to each other. But so that's at n equal to 1, right? So there's, let's say, n equal to 1 over there. So at that point, the lift has to be equal to the weight. For other values of n, it will be a factor of n times the weight, right? Because that's the definition we gave for this, L by W. So when L equal to W, that will be equal to 1, right? So that's the stall that you're talking about, that particular point at which this happens. And of course, that is the minimum speed that you have. You can't cruise below this particular speed. But that minimum speed is different at different n factors, because this changes. Your lift changes. Lift was equal to W. Now it can be either more than W for points above this particular point, or it can be less than W for points below this, which means that this becomes, because there's a square involved, remember, there's a square that is involved over here, and your L by W is what is n. Therefore, you would have a quadratic curve like this. Similarly, there's something called a negative stall, and therefore you would have a curve like this. Okay, so whereas these are straight lines usually for most aircraft, these are curved lines that are coming because of the square behavior, and your L by D, the W ratio is what is your n. So in other words, I can write this as n times W in a very general sense. It's equal to W only for on this particular line, but for all other points on this graph, you would have L is equal to n times W, right? So sometimes n becomes negative. What does it mean? There's a negative lift. In other words, the aircraft is getting accelerated downwards, or in other words, perpendicular to the velocity, but more towards the earth, right? So whatever is over there, it's very clear that the n and v are related. One side it is linear, the other side it is quadratic. So that's why you get this particular behavior that you see over there. Is this clear? Okay. So now, as structural analysts, when we are trying to deal with a problem, this has to be given as an input for us. The Venn diagram is very, very critical input for us structural analysis, because then we can know these points. Okay, so we will typically check for these points if the structure that we are designing is really safe enough. Otherwise, we have to change the material and or change the geometry, either the shape or most of the times it's sizing. Let's say some structural component has to be thicker than what we were already using, so that it's able to distribute the stress in a lesser way, in a less concentrated way, and therefore you will be able to handle these kinds of situations. So how the Venn diagram itself is arrived at, of course, again, there's an interplay between the structures and the aerodynamicists, because it's only the left and right boundaries that are dictated predominantly by the aerodynamicists, whereas the top and the bottom are dictated by us structural analysts to some extent because of the choice of materials that we take from a structural point of view. But some things are beyond that, because if it's a human being involved or the avionics involved, etc., again, that is beyond our control. So all that we have to ensure is, given this Venn diagram from the overall aircraft design, predominantly from aerodynamicists, but not necessarily only that, the other aspects coming in, we have to make sure that all the end points of this are safe from a structural point of view. So our decisions on the material and the geometry have been made appropriately. Within the geometry, the shaping and the sizing are made appropriately, and within that, because there are multiple components, their joints are also made appropriately, because many a times the component may not fail, but the joint between two components might fail. So you have to, for example, the fuselage, the way it is attached to the wing, there could be a failure there. The wing itself might not have failed, the fuselage itself might not have failed, but the interface is failing. It's still bad enough, right? So you have to make sure, and these joints, of course, become even more intricate when we go into the internal skeletal structure of the construction of the wing itself, or the fuselage itself, or the horizontal vertical tails themselves, because within that you have so many more joints. There are smaller and smaller parts, structural parts, which are all joined to each other, and you want to ensure that those joints don't fail as well, right? So that's one thing. Now coming to the last entity over here, the internal pressurization. The internal pressurization is something that, as I said, because at higher altitudes the pressures are lower, and it's not only the human beings but also the avionics and other systems will not function at their optimal functionality unless and until a certain level of pressure is maintained. So you can't afford to maintain the sea level pressure, because that's quite expensive in terms of how you want to construct the fuselage. But you arrive at some kind of a intermediary. It's neither the ground pressure nor the pressure at which the aircraft is cruising, but somewhere in between where it is still comfortable for human beings, and depends upon the type of aircraft that pressure is decided. So, and that pressure is maintained throughout the flight of the aircraft, so that you ensure that people are comfortable inside, the crew is comfortable, and also just like the G can make a huge difference in terms of how we work, the pressures can also make a difference, though not to this extent. Okay, so that's essentially the small ranges within which we can work, the temperatures. We adapt when you guys come from a colder place to a hotter place. Over a period of time, our body tends to adapt to those new situations, but there's a certain limit up to which we can adapt. If it's too high a temperature, maybe even with practice it becomes almost impossible, because of the very nature of how our physical body is constructed, its cells and the tissues, how they behave, right? So same thing with the case of the aircraft as well. And therefore, once you have an internal pressurization, so what you're having is in the aircraft fuselage, so this is internally pressurized, right? So within that you are having a certain level of pressure, because of which this becomes like a pressure vessel. Okay, so you're familiar with let's say high pressurized gas or liquids are stored, let's say liquid nitrogen or liquid hydrogen, etc. When they are stored in a cylinder, there's a certain pressure which results. And so in the mid portion, for example, if we take that to be just a cylinder, you know, because of the light weighting that we have already discussed, we want everything to be light. So this is going to be a fairly thin cylinder that is over here, right? Now that with the internal pressure that it has, so if I cut out a cross section, of course there are cutouts for the windows and the doors, etc. Those make the thing very complicated, but nonetheless to keep things simple at a particular cross section where none of those other things are there, essentially what you're looking at is a pressure distribution on the inside, right? So you're maintaining a particular pressure. Of course there's also the ambient pressure, which is much smaller because you have gone to a higher altitude, so that pressure is very small compared to the pressure that is coming from which we are applying in the interiors, right? Now most people will think about this very simplistically from a layman's point of view. What is there over here? The interior obviously is having a boundary condition of a pressure which is equal to this big P, and this is equal to, let's say, the P atmosphere at that whatever altitude is there, whatever altitude we are flying at. Let's say cruise, if it's a cruise condition, then it's essentially at cruise. Okay, so then you would see that all the points on the interior are going to be stressed in the radial direction equal to this P, because that's the boundary condition over there, and outside the boundary condition is P atmosphere. But that's not all. In fact, a much more dominant load comes as what are known as hoop stresses, and also to a lesser extent the longitudinal stresses. Okay, so the hoop stresses, if I were to cut this cross section over here, then you would see that on this circumferential section there's going to be a normal stress that is coming over here, and in this coordinate system of r theta z, where z is along the axis of the cylinder, r is in the radial direction, and theta is along the circumferential direction and angular measure, then this is what is known as a sigma theta theta, and we'll come to how these notations are, though you might be familiar with from the previous course. But right now for this particular purpose, this is what is known as the hoop stress, and this is given by that if this is very small compared to this, you can just ignore that, and what you have is essentially if the thickness of this thin walls is T, then it is the pressure, big P, which is applied inside over here, and that times the radius, which is the mean radius over there, divided by the thickness. That's essentially the kind of hoop stress that will come. Now you see that there's a factor of r by t that is coming, and if it is a thin walled thing, you know that t is very small compared to r, and therefore r by t is much larger compared to 1. So that's like an amplifying factor for your pressure. As a layman, we thought that yes, the boundary condition says there is a pressure P, so that's the stress, which is essentially your sigma RR, which is true. Your sigma RR is equal to P on the interior surface, and it's on the exterior surface, your sigma RR is equal to that small p atmosphere cruise that we talked about, right? But this is very small compared to this, and this is this is small compared to this. So in other words, the dominant stress that is coming is sigma theta theta. Okay, so this is again an example of the dyadic that we talked about, the inertia dyadic and the mass dyadic, which need two directions. So what are the two directions in this case? Theta and theta both. Why we need to mention that twice? One is because you are cutting this, remember, over here and trying to take a look. So the normal to that is the angular direction, theta direction, right? And also the direction in which the load itself is acting is also the theta direction, and therefore there are two thetas required. The first one to say on which surface it is acting, the second one to say in which direction the force itself is acting. Therefore you have this. If there could in some examples there could be a stress in this way, so then it's a shear stress acting on that surface. Once again it's acting on the same surface, so therefore the first subscript will still remain theta, but the second subscript will now be in the r direction, the radial direction. So this will become sigma theta r. So whenever the subscripts are different, it becomes what is known as a shear stress, which is next to negligible in this particular case, whereas unless of course the kind of materials that are involved bring in a coupling, especially composites. But here this is an example of a normal stress, because both subscripts are the same, theta and theta, right? So similarly here also both subscripts are the same, r and r. So this is a normal stress. So similar on the other hand, if you have a theta r or a theta z or an rz, those are all other examples of shear stresses. You could have similarly you could have theta z or theta let's say rz, right? And of course if you interchange that, the actual physical meaning is different, but we will also see under certain special circumstances, which almost holds for all materials that we would be interested in. It doesn't matter whether you put rz or zr, okay? But from the point of view of the definition of how we put the subscripts, the first always stands for the normal to the cross section on which the stress is being observed. The second always refers to the direction in which the load is acting on that surface and therefore creating the source of the stress. So is this clear from the internal pressurization point of view how things get affected? So from the fuselage, within the fuselage you need to have a certain pressure which is not as high as the sea level atmospheric pressure, but not as low as the cruise altitude pressure, atmospheric pressure, but somewhere in between where you can have a reasonable comfort for the people as well as the avionics and other things involved. What happens when you want to make it very comfortable and have it the ground level pressure? Obviously these stresses go very high, which means that if I have to design the fuselage for that, I have to make the thickness of this fuselage shell much more, and the joints and other things that come into it, which means a penalty of weight for the fuselage and penalty of weight therefore for the aircraft, which means that more fuel consumption, or you have to take less people within, etc., etc. Okay, you might sometimes make that kind of a compromise. For example, if it's instead of a cattle class economy alone kind of an aircraft to, let's say, an executive aircraft, you really want the people inside to be very comfortable, you might sacrifice in terms of the number of people you can take and instead make this thicker shell so that you can afford to have a pressure which is equal to the sea level atmospheric pressure inside, so that you are pressurized. So it is undergoing larger stress, but because it is thick enough, it's so essentially it's this factor is P by T. For the given size of the fuselage as a whole R, it's essentially a linear dependence between P and T. If you're taking the same material, you know that it's going to fail at a particular value of the stress. So you want to keep that a certain margin of safety below that. So this is the maximum that you can go to is the same. But if you want a higher pressure and more comfort over there, higher pressure all the way up to the atmospheric sea level pressure. Otherwise, if you go much beyond that, again it becomes uncomfortable in a different way, right? But when you want to increase P, obviously you have to increase T if you are keeping the overall size of the fuselage the same, right? But the thing is, in most executive kind of an aircraft, it will be a smaller aircraft, and your R will be also fairly small. Okay, so sometimes you might have a trade-off between these two, going from a large passenger aircraft for which R is large and therefore P has to be small if you are keeping T the same, and then you want to see for an executive aircraft R becomes small, and therefore you can probably increase P without the failure happening, because you're still within the failure limits for the material. So these are all the design trade-offs that you have in terms of what are the user's requirements and in terms of what is the structural requirement that we provide. To a large extent, even R becomes a user requirement because they want a more spacious kind of aircraft, or more number of seats in the case of an airline wants to maximize the income it gets from the passenger tickets, etc. Then obviously your R is defined based on that. Okay, so the only thing that we have total control over as structural analysis is this little t that you have at the denominator. That's what we can play around with depending upon what are the requirements from the overall design point of view, right? So do you have any doubts either on the Venn diagram or the internal pressurization? Okay, let's move on.
Sure, I fully understand like how the theta stress works, like what causes it.
Okay, very good question. Okay, so for that you have to go for the equilibrium equations. So let me. Now suppose I cut this instead of the way I've cut over here, right? Instead I cut it like this, so you have half a cylinder, right? So, and I plot the cross section of that, then it's going to look like this, right? So I've cut it in half like this, and then I'm seeing from one of the along the axis of the cylinder, right? So when you have this, as we already pointed out, we have this large P, the internal pressurization that is there over here, right? And because we have denoted the radius as R, this whole distance becomes 2R, right? Now this is essentially a load which is exterior to the structure. Though it's internal pressurization, it's compared to the structure, it's a load that is applied. So in other words, something coming from its environment. Okay, now that portion of the structure will have to resist that. Okay, so now we go to Newton's third law. Every action has an equal and opposite reaction. The action that we are talking about is this guy, right? What is the reaction due to that? That is the stress. Okay, so this is a generic thing. Whenever you have a load, you have a reaction of the material of the structure to that, and that's what we call as stress. Okay, so in this case, what is this P trying to do? If you take the let's say the resultant of that, there is if you take this portion, there is an upward thing. If you take this portion, there's a downward force. So they are balancing each other out if it's perfectly circular, right? On the other hand, because of the way we have cut, we see that there is an unbalanced force which is coming in this direction, okay? And that is equal to your pressure times your 2R that is coming over there, right? Now that is trying to push it to the left, right? Now here you have that reaction according to Newton's third law, which is coming, which is trying to, if this is trying to push it this way to the left, that is trying to pull it back to the right, so that the balance remains. So this is your sigma theta in order to counteract that. Now you have to go to your equilibrium of this, and for a unit length along the cylinder, you multiply this by the area on which it is acting, and then you have to equate this to the area on which this is acting, because this is a thickness T, but there are two of them on this side and this side as well. So essentially you have sigma theta theta here as well, which is acting on, this is thickness is T, right? So your sigma theta theta into T into along the length, a unit length, so 1, right? So your sigma theta theta, there are two of them, and multiplied by the thickness and multiplied by unity, right, along the length. Okay, now that you're equating to your P times 2R times once again 1, right? So when you're equating those two, you see that 2's cancel out, and then you have sigma theta theta is therefore equal to whatever we wrote over here, right? So similarly, instead of cutting along the length, that way half of the cylinder, if I cut this way like the way I had shown earlier, you can get what is known as a longitudinal stress as well, and that's essentially acting in the z direction. So there will be a sigma zz as well in this particular case, and that you can show very easily to be PR by 2T. In other words, it's a half that value. So you can just do it as an exercise. If you get stuck up, just it's not a homework, it's not an assignment, just if you can, just the way I derived this, if you try to cut it over here, and then you're doing the same analysis what we did over there on a cross section like this, and you see that there are the loads which are coming because of the longitudinal stresses, because sigma zz is on a surface to which z is the z direction is the direction of the normal, which means that it's this cross section, and the force is also along z. So just like sigma theta theta is a normal stress, this is also a normal stress because the index is repeating. And on that, what is the equilibrium that you need to do? For that, you typically what you do is you fix a cap or a head to this, and on that cap, what is the pressure that is acting? This is the same P, and that P is acting on an area which is equal to pi r squared, right? So P times pi r squared has to be balanced by this, which is acting throughout the circumference, which is 2 pi r times the thickness, which is the area on which it is acting, times sigma zz. When you cancel out things, this is what you would end up with, right? Any other questions? Either on the internal pressurization and or the VN diagram. Okay. And this will be very different if it's a passenger aircraft or an acrobatic aircraft or a fighter. Okay. So for example, you would probably get this spread out in the case of an acrobatic aircraft, and even more spread out in the case of a fighter aircraft, right? And similarly, if you're looking at subsonic, supersonic, etc., obviously you're pushing this right boundary outside as well. So it becomes all the more challenging for us as structural engineers to design components for faster aircraft and or highly maneuverable aircraft, because the stresses can be very large. So you need to have material choices and geometry choices, both shaping and sizing, which can account for that and still be safe, so that for all the kind of things that you not only normally fly but can expect in an emergency or anticipate in an emergency kind of situation as well, you will have to make sure that the aircraft is always within this envelope, not outside. Okay, done. Let's go to the next. So that's as far as the classification of flight vehicles based on the loads is concerned, depending on the source of the load. Now we go to the other end of the Newton's third law, the reaction instead of the action, and that's talking about the resultants of these sources. Okay, because instead of dealing with the complex nature of these sources, like for example airflow, we talked about the airfoil, how the pressure distribution is, how the shear distribution is, but we might as well deal with just lift, drag, and pitching moment becomes much simpler. So that's an example of going from the actual behavior to a resultant behavior, and that's where the resultants come in. And the resultants almost always are in the form of forces and moments, as we already saw in the case of, let's say, the weight distribution. There is a weight which is coming, which is translated to the root where the wing is attached to the fuselage, and also a moment because of that, because of the moment arm which is non-zero, and therefore it's causing a moment as well. So that's essentially the what we are talking about. Now within moments we can have two types. One is the torsional moments, the other is the bending moment. So essentially, you know that a torque is something like this, which is trying to twist the structure, whereas the bending moments are those which cause a flexure. In other words, it's flexing in such a way that some fibers are extending, some fibers are contracting. So that's essentially flexing. It's a common word which is used in a colloquial context also, like flexing your muscles. So essentially what you're trying to do is to bend. So that's what we are talking about as the bending moment over there, and the torsional moment. But at the end of the day, if you go back to that D'Alembert's version for rotational equations of motion that we wrote, where we said that T minus I alpha or M minus I alpha equal to 0, you would see that both of them are taken into account in the same equation. But in terms of the overall behavior, there will be a subtle difference, only because we are, in the case of light vehicle structures or any transportation structures, we are no longer dealing with three-dimensional brick-like structures, but those which are either plate or shell-like structures on the one hand, or the beam-like structures or one-dimensional structures on the other hand. Therefore, the behavior is very different. Otherwise, from the pure physics point of view, they are one and the same. It's only because of the large difference in the dimensions in different directions that the behaviors become very different from these. Okay, so one, we have to understand it from a bigger perspective as to what their commonalities are, and the other, going to the specific components on which it is applied, what are the differences which come out, and therefore how the overall analysis or design changes. Coming to the forces, once again, just like we discussed with the stresses, the source of that stress in the first place is the force. And that force, just like the stresses of two kinds, normal and shear, your forces are also normal and shear. So anything which is trying to act in the same direction as the normal to this cross section is essentially a normal force, and anything which is perpendicular to the normal, which is acting like this, is essentially a shear force. So those are the two things that you have. Again, in terms of normal forces, depending upon the direction, I can either pull it or push it. In other words, make the fibers to extend or to contract, based on which I have either extension or compression, right? So two kinds of normal stresses or normal forces that are there from a load perspective. Now coming to the shear, again, this is a very subtle difference most people will not be aware of at this level, is in terms of in-plane and transverse. So what is this difference over here? If you're talking of, let's say, this table top that you are having, and you have put all your laptops on it at each point, because of the size of the table compared to the sizes of your laptop, it's very small, so it can be treated as concentrated loads, okay, for a first cut analysis. Otherwise, you have to look at a distributed force along that particular whatever the area, or many of these, because of the airflow, they will not be, the entire surface will not be in contact with the thing. There might be four rubber pads at the four corners, and essentially over the surface area of those rubber pads is what the weight gets distributed, more or less equally, but depending upon the where the battery is located on your laptop, etc., it might change. But whatever it is, all of these are weights, which is the downward force acting on this tabletop, and it has certain supports which has its legs along the length and two along the width as well, and there is a reaction which is coming from the ground which is helping it to push it up, right? So there is a force, because this is not moving, at least with respect to an earth fixed reference frame, this is not moving, which means that it has to be in static equilibrium. There has to be a force equilibrium, there has to be a moment equilibrium as well, right? So when the moment equilibrium comes into picture, then the distance, exact location at which you have put your laptops or your water bottle and things like that. All of that comes into picture in terms of calculating the moments that are involved, right? Now, this force, the predominant thing that it is going to do is to bend this tabletop, okay? So you have, it's not very clearly visible now because your laptop weights are so small, thanks to the laptop technology is increasing so rapidly. But if you put a very heavy, much heavier object in between, you could see actually there is a curvature here, and which is what happens in your aircraft wings when you see a huge tip deflection that is happening because of the lift that is generated has to be as equal to the weight of the entire aircraft and all its contents, right? So obviously it's bending much more, almost visually you can perceive that it is bending, okay? Now that is the primary effect, but there is also a secondary effect of the shear force. Now those total weights are all going to, at this particular end where it is attached, are going to cause a force in the downward direction. So if I cut this table over here, imaginarily of course, I would see on that cross section the reaction, again going back to Newton's third law, those weights are the action. Now this is the reaction. It has to offer a stress in this particular direction. Now, if you look at the cut, it's along the length, okay, which is a large dimension, okay? And if you're looking at the stress, it is along the thickness, which is a very small dimension, okay? So now when you have a combination of a large dimension and a small dimension, these are the guys that you're dealing with, the transverse shear stresses, transverse shear strains. On the other hand, if I'm trying to pull this table over here, I'm causing a load along the length, and this is, you are trying to hold this and I'm trying to pull this way. Obviously if I cut along the length now, on that cross section, you would see that there is going to be a stress, a shear stress which is going to be there. Now that stress is acting on a cross section which is perpendicular to the x2 direction. If this length is x1, the width is x2 and the thickness is x3, it's along the x2 direction I made the cut, right? But now the stress itself is acting along the one direction. So both, it is sigma 1, 2, and both these are large compared to the thickness. It's the third direction, the thickness, which is small, the width and the length are large, right? So when both the dimensions involved in your shear stress are the larger dimensions, that kind of a shear stress is called as an in-plane shear stress, okay? And there's a huge difference in the way most structures will behave based on whether it is in plane or transverse. And for a large class of problems, the transverse stresses will be very small compared to the in-plane stresses, but you can't still ignore them because they become the cause of a lot of failures, especially in composite laminates, because you have a laminated structure. In other words, even this plywood, for example, it's not made out of a single layer. There are many plies which are put together, attached to each other through some adhesive, and therefore there is a stress within each one of those plies, and there is also a stress between those plies, both shearing stress as well as normal stress, and that shear can cause what is known as delamination. And remember that that particular stress that we are talking about is it's on a section which is having the x3 or the thickness direction as the normal, and therefore whether it is in the one direction along the length or in the two direction along the width, in both cases it's a transverse shear. So that transverse shear can cause two layers which are adhesively bonded to get debonded, what we call as delamination, okay? Because it's a laminated, opposite of laminated is delaminated or delamination that we are trying to have. Now that need not only be caused by transverse shear, I'm talking about that because I'm introducing this particular concept, but it can also be caused by what is known as a peel stress. In other words, just like when you're peeling a banana, what are you doing? You're essentially trying to pull these two layers apart, right? So that's essentially a normal stress. So you're trying to apply on the x3 surface a load or force in the x3 direction. That's what you're trying to do when you're trying to pull it. So it's a sigma 3, right? So that's a normal stress, but it's a transverse normal stress. This is a transverse shear stress. This is also a transverse shear stress. So there are three sources of delamination, which is one of the major failures of composites, which are a major constituent of most aircraft today, is the peel stress and the two transverse shear stresses. Even though they are very small compared to all the other stresses, why extension and compression come? It's because of the bending. We already saw that the lift distribution, which is equal to or much more than, it can go all the way up to n max times the weight of the aircraft, is trying to pull it up. So it is bending such a large with such a large moment that it is going to cause the top fibers to on the upper surface of the wing to get contracted, right? So in other words, there's a compression on the top. At the bottom surface is going to get extended. There's a tension. So there you can see there's an extension, there is a compression as well. So in fact, these will be the dominant loads that we'll have to design for, and there will be in-plane stresses as well. That is the in-plane shear that I talked about as well. That will typically be caused by various sources. We'll get into that when we reach there, because it's a little more complex. And then the transverse shear stresses, because even though this is much smaller compared to your in-plane shear stresses, compared to your extension and compression normal stresses arising primarily because of bending, but also in helicopter rotor blades, it's not only the bending but also the centrifugal forces causing the axial load. So over and above that, the axial stresses, the compression and tension from the bending gets added or subtracted, and therefore you will see different experiences of the different layers on the top all the way you go up to the bottom. And the same aircraft, it's not flying, let's say it's on the ground, it's in the hangar, or even if it's taxiing, you see at very low speeds, you see that it's mostly self-weight. So it's bending in the other direction. Now the top surface of the wing is getting extended, the bottom surface is getting contracted. So in other words, it's through every flight that this takes, depending upon whether it's a long haul aircraft or a short haul aircraft, it is going through different periods of these loads in an overall sense, because of the various phases of flight that it goes through, from the hangar, taxiing, takeoff, climb, cruise, descent, and land, and again taxi, whatever. And in between, of course, more complicated aircraft like fighters, the maneuvers, or the acrobatic aircraft, the maneuvers that they do, right? So in your analysis, you have to make sure which part of that you're designing for. Go to the VN diagram that you see over here. Get the more critical points over there for a particular component. What is critical for one component may not be critical for the other component. So you have to make sure each and every component you check out from all the boundaries of this VN diagram to make sure you're doing the design for the most critical case. So that way all the other cases will be automatically taken care of. The margins of safety will be much larger over there. Okay. So I think with this we kind of complete this. I do not want to get into the next slide because it will be a different topic. If there are any questions, I'd be happy to answer. Okay, good.